Hello. I think everything looks okay. Is everybody there? I'm setting things up. Okay. Okay. Let's see. Okay, so we're going to keep on looking at some examples of using closures. Okay, I want to do one more. We haven't really gone through these sorting examples. I think those are interesting examples, and it bring up some interesting topics in programming languages. Okay, so we're going to look at these examples on sorting. Okay, and I've got this folder here. Here's the code. The sorting is written in, well, Racket, language 9. Could actually do the sorting in language 9 or in Java. Okay, and it could do this in lots of languages. This is actually a really good exercise. Okay, let me show you. Okay, remember we talked about the idea of this the other day. If I have this little data structure, there's lots of ways I can sort it. Okay, so I can sort it by I can sort it alphabetically. I can sort it numerically. I can sort it numerically on this column or this column. I can sort ascending. I can sort descending. I could even do unusual sorts. Like, what if I want to sort by the sum of these two numbers here? You know, what's to stop me from sorting by the sum of those two numbers? So I can come up with lots of ways of sorting this data structure. So I don't want to write umpteen sorting functions. I want to write one sorting function that's generic. It will.
All you need to do is just write the comparison function.
Yeah, and so here's a way to think about it. You're used to the idea of a function taking in data. So you have a function of data, okay? And the data usually, just something like f of x, So you have a function that takes in, and this is the data is the parameter. Okay, but in truth, functions can have a lot more. There's a lot of other ways of giving a function parameters. Like here's kind of an abstract way of thinking this. The function can take in some data, but then it can also take in something that tells it the type of the data. Then it can also tell us something to say how to manipulate. Okay. So imagine a function that has that can be that these are all parameters to the function. The function takes in some data, but then it takes in something that tells it what the type of the data is, and it takes in something that tells it how to manipulate the data. Okay, these are ways of making functions generic. In Java, you have something like the following. Actually, I can show it to you even online. If we look up the Java arrays, go down here to sort. Look at this row here. Okay. Compare it to what I was just writing over here. I have a function, abstractly it's defined something like this. There's a type T, and then you're going to sort an array of T elements, and you're going to and then that's the data. And then you're going to use a comparator that knows how to compare type objects. Compare. Okay. So this is what the Java function definition looks like. Now notice there's 3 parameters in this sort function. This guy is the data. That's this one here. That's the thing you're used to. But notice that there's this parameter here showing up as this thing here. This is Java's notation saying that this sort can take in different types of data. So in a sense, if I look at this, there's another parameter to this function. This function's got a type of the data parameter. Then this function has a comparator function that tells me how to manipulate the data. So the function has got 3 kinds of parameters. It's got the actual data. It's got the type, and it's got what's sometimes referred to as the behavior. Okay. So we've got a data, a type, and a behavior parameter to the function. And in Java, it shows up as data is a regular parameter, type is this generic parameter that's over here, and the behavior is a special object you pass that changes how you sort. This is the thing that determines whether this is the thing that'll decide whether we're sorting on this column or this column or this column, and it'll decide whether we're sorting ascending or descending. That'll be in the behavior, the thing that decides how to manipulate one of these pieces of data. So it's an array of country elements, and this guy says how to compare country elements. Okay? So in the world of programming language, we're talking about generic functions, and we're talking about all the different ways that you can parameterize generic functions. You're used to parameterizing with a parameter. Okay, that's the easy kind of parameterization. The function can take in a different piece of data. I mean, if you think of just the simplest thing, f of x equals x squared, the squaring function. Okay, that's a real simple function. It takes in numbers. It just says squaring. You can square 2, you can square 3. Okay, there's nothing generic. There's nothing that's the only parameter there is the actual value of the function. But in general programming, we want to have functions that are far more elaborate than this. We want functions that take in data, but we want to be able to say what the type of the data is. So, for example, I could sort an array of integers, but at the same time, I should be able to sort an array of strings. I should be able to sort an array of doubles. So this guy is saying that sort isn't, like if you go over here, in the old-fashioned way of doing things, you had to have sorting an array of float, separate from sorting an array of int, separate from sorting an array of long, separate from sorting an array of short. See, they had to actually literally write all these different sort algorithms. That was before Java had become really before they thought of a good way to make generics. Okay, so you don't want to have a gazillion sort functions. You really want to say that this sort function can be told what the type is. Changing the type, like sorting arrays of ints, is not the same thing as sorting arrays of doubles. Here, this is one function, and this is a different one. They're written differently, okay? In this scheme here, this is actually many sort functions, but it's written one way, and at compile time, the compiler actually will, depending on the type here, the compiler will spit out the appropriate code depending on what that type is. There really are multiple sort functions, but you don't have to write multiple sort functions. The compiler writes them for you. This is the magic of this modern way of doing things. Instead of you writing a version of sort for ints, and a version of sort for longs, and a version of sort for shorts, using modern Java generics, you can write one sort function that takes a parameter t, and then the compiler will make the changes needed to give you all these different sort functions. So in the compiled code, there will be, if you call sort with, if you call sort on an array of, okay, if you have a, if you have an array of ints and an array of doubles, and you sort the array of ints, and you sort the array of doubles, okay? From your point of view, that's one sort function. But from the compiler's point of view, it's two different sort functions. It'll actually spit out one set of code for this and a different set of code for that. Okay, but you won't have to write these different sort functions. You won't have to write these different sort functions. The compiler more or less does it for you. But the compiler sees that A1 is an array of int. In fact, I mean, in true Java generics, I have to make that integer and double, because you can't do this with primitive arrays. So that's why they still have these, because if you're really working with primitive arrays, you have to call you have to literally call all these different functions. Okay.
You can pass Java generics arrays of primitives.
Yeah, because of auto boxing. Yeah, but the compiler actually converts them to arrays of non-primitives. That's called
I thought
auto
it would
boxing.
just see it as an object, and it's like, oh, you gave me an object. Okay.
No, it converts it, but it auto boxes them. So it has to convert it to one of these. Now, if you actually do it with an array of ints, it'll call this sort function. It won't call the generic one. So if you give it an array of doubles as primitives, it'll call that function. If you give it an array of doubles like this, it'll actually call the generic one down here with an array of doubles, where t will be double with a capital T. So if you actually give it an array of of primitives, it'll call that version of the sort function. If you give it an array of what do you call these guys? Wrapper classes. If you give it an array of wrapper classes, it'll call the generic one. But these are not the same sort function. They're really not quite the same sort. Just like this is not the same sort function as that. Okay. But somebody actually wrote this out in hand, and somebody wrote that out in hand. These are all written out. Okay. This is not the same sort function, and this is not the same sort function, but the compiler spits them out. The compiler uses the modern Java generic system to spit out two different implementations of this. Where is it? I lost where the, yeah. It spits out two different implementations of that function, one for type integer and one for type double. Okay, so this is one form of generics on the type. So the type of the data is actually a parameter to the function, but you write it outside, you write it in a weird way. Notice that parameter in Java syntax sits out in front of the function. So you say sort takes a parameter, a type parameter, and then the type parameter is used inside here. Okay. Now the behavior is just Java doesn't need anything really special for that. The behavior parameter just is a regular parameter, but it's a function parameter. It's a function that this function makes use of. So this becomes like a helper function. This is a behavior function. It's a function parameter to a function. So this is the modern way of doing programming. This leads to the functional style of programming, that you're parameterizing your functions with behavior functions. Sort is the classic example, and even C has this. I mean, we saw that you could even go back to the C language. C had oh, I'm sorry, not sort Q, it's Q. the sort function, even in C, took a function parameter, okay? And also, they did, remember we talked about this the other day in class. C does have the type parameter there, but in a very strange way. The type parameter is there because it shows up here as a pointer to void. So the type parameter is there. This function has a, but you're never declaring it. You're just saying this function takes some pointers to something. And as long as that pointer and that pointer agree, the function will work okay. So there really isn't anything saying exactly it's an array of int or it's an array of double. The QSort never knows. And it's up to you to make sure that that pointer to void is really the same thing as that pointer to void, and then the QSort will work well. In Java, you actually say that the type here and the type here must agree. That if you give me an array of integers, you better give me a comparator of integers. In C, you could actually screw it up. This could be a comparator of doubles, while that's an array of integers. Java will never notice the difference. I'm sorry, C will never notice the difference if that's an array. If that's an array of integers and that's a comparator of floats, especially since arrays and integers and floats are both 32-bit values. If this is a comparator of floats and this is an array of integers, there's no way C would know that there's anything wrong, okay? Whereas in Java, you say that you have the type of the data, and that type of the data is also used by the function here. So here we see that the type of the data is a parameter there, and it shows up here too. Okay? But notice that the key idea is that we're parameterizing a function the classic math way. There's the parameter to the function, the data. But then there's a sense of, well, what's the type of the data? This function should be able to work with different types of data. And then exactly how do you want me to treat the data? How do you want me to compare 4 and 5? Which one is the smaller? If you give me a less than operator here, 4 is less than 5. If you give me a greater than operator, 5 is really the one that goes on the left would be 5 if you use a greater than operator. Okay? Which one makes the operator, the true value of the comparison operator switches when you use a less than or greater than. So this one decides how to sort the data. In this case here, the comparator is deciding how to sort the data. Okay, so in modern programming language, this all falls under the notion of polymorphism. Okay, but there's many, well, and this is the word, let's see, polymorphism in computer science. See, polymorphism over here in computer science. Okay, is this idea that you can write functions that have more parameters than just the idea of the classic parameter. It isn't just the function. It isn't just the usual classical parameter of the function. That's this one here. But then there's also type information and behavior information. Okay, so that's our basis for what we want to do with the sorting. Now, in Scheme is like C. It doesn't have really type parameters. So in Scheme, you don't have this middle one. Java has the middle one, and C++ has the middle one. That's this part here. Scheme doesn't have them. Scheme would just have the data and the behavior. And it's up to you to make sure that the behavior matches the data. Just like in C, you got to make sure that if it's an array of ints, you're comparing ints, not comparing strings, because Scheme won't know the difference. If you goof it up in Scheme, you could give it an array of strings and then give it you can give it an array of strings and a comparator of ints. Scheme won't know the difference, like C, but Java would. Okay. Now, in Scheme, we saw what the code looked like last week. Oh, I have it up here. It's not so easy to read this because it's getting to be kind of abstract code. The sort function takes in a list and a function that compares. So there's a data parameter and a behavior parameter. The behavior parameter says how to compare the items in that list. It's up to you in Scheme to make sure these two guys agree with each other. If that's a list of strings, this better know how to compare strings. If that's a list of integers, this better know how to compare integers. Okay, so just like in C, it's up to you to make sure these agree. Okay, and then we did, this was a recursive insertion sort. Okay, so it uses two nested functions. There's the insertion function, there's the sort function. The sort function calls the insertion function. The actual sort function I'm writing just calls the recursive sort function with the list. Okay, all right. So this function here defines a local insert function and a local nested sort function, and it calls the local nested sort function with the list. The nested sort function takes in a list, and then it checks if it's empty. The sorting of an empty list is empty. Otherwise, it inserts the first element into the list into the sorted rest of the list. That's the recursion. To sort a list, you take the first item and insert it into the sort of the rest of the list. Now, it's the insert that needs to know how to do the comparison. Notice that there's no mention of the comparator here yet. Okay, the comparator is up here is this. This is the to this body of code here. This is like a global variable. So everybody has access to the comparator. The insert function is going to actually, at this point, use the comparator. So this is where the closure comes in. So this is where we're using a closure. This is a function that has a non-local reference, and its non-local reference is closed by that guy there. Okay, so the closure just makes it easy. It makes it convenient for us to write this code. We don't have to keep passing the comparator as a parameter. We don't have to say, and pass the comparator to that, and pass the comparator to that, and then pass the comparator to that. See, we don't have to keep passing the comparator along all the time. If we didn't have a closure, we would have to keep passing that parameter around, okay? But as it is, because this guy's sitting here and he's in the outer scope of this function, everybody inside here has access to the comparator. So when the insert function wants to use the comparator, it has access to it through the closure. And then the comparator just says, if you give me an empty list, I just put the item into the empty list. If you give me a non-empty list, I compare the thing you gave me with the first item of the list. If it's smaller than the first item of the list, I put it at the front of the list. If the thing you gave me is not smaller than the first item of the list, I cons the first item of the list onto, well, you insert the item you gave me into the rest of the list. Okay, so pretty simple, not fast, but simple way to write sort. Okay, and then down here it gets a little bit interesting. We need comparators. Okay, now here's we've kind of directed the problem to another layer. If I sort this thing here, I want to write one sort function. I have that. And that sort function can, depending on the comparator you give me, it can sort the function on, if the comparator looks at just the first field and compares strings, I can sort by strings. If the comparator looks at the second field and sorts by numbers, I can sort by numbers. If the comparator takes the sum of these two fields, I can sort by that. Whatever the comparator does, I'm sorting by that. Okay, so I only have to write one sort function. But notice I've now burdened myself with writing lots of comparators. Okay, for example, I would have to write a comparator for comparing the first field. I would have to write a comparator for comparing the second field. I'd have to write a.
It's only one line of code, though.
Maybe
two.
Yeah, but the thing is, I don't want to write all those comparators. I want to now parameterize the comparators. So I'm going to, this is the fun of functional programming. I keep saying that I don't want to have to keep writing multiple chunks of code. What I want to do is I want to write functions that write comparators for me. Okay, so I'm going to define make comparator. I'm going to define a function that makes comparator functions. Okay, so this is really kind of nice. What I'm going to do is I'm going to define a make comparator function. Okay, now at this point I didn't do it too abstractly. I have one that make compare by area and make compare by population. In fact, I could have blended these two together, but right now I'm making two. These are sometimes called comparator factories. This is a factory that returns comparator functions, and it compares by area. Now, what's there to decide? If you're going to compare by area, you could sort ascending or sort descending. So what this really does is it makes two different comparators, depending on whether I want to sort ascending or sort descending. So this comparator is a function that takes in another function, and it returns a function that takes two countries and compares them by this parameter here. See, this parameter is the thing that really compares. This thing is a get function. It gets the area, out of the country and gets the area out of the other country. Okay? So I define a function that takes in, now this is going to be either less than or greater than. See, make compare by area less than, make compare by area greater than. Okay? Now actually, let me show you a little bit better way to write this. Here's a little bit more generic way still. I just want to make compare. And then I'm going to give this thing two functions. I'm going to give it a compare function and a get function. And then it'll get from one country and get from the other country. And now this thing can generically do, it can make a by area comparison, or it can make a by population comparison. So then I can shorten my code down over here, and I could now do the following. I'm going to sort countries. Oh, I'm sorry. That's the wrong. That's the more verbose. I wanted this one here. I want to change this one. Make comparison less than get area. Make comparison greater than with get area. Make comparison less than using get population. Make comparison greater than using get population. Notice that my code ends up being much more compact. Notice instead of having to write two comparison functions and then call them this slightly more verbose way, notice how my code is starting to get very elegant now. I can sort countries by, well, make a comparison on less than on area, or greater on area, or less than on population, or greater than on population. When code is written like this, it starts becoming very elegant. This is what people mean by real functional programming. I have a factory method, a single factory method now, that's more efficient even than these two factory methods, that it sorts by, it has the factory method builds the comparison function given an ordering and a field. So I say what ordering to use and what field to sort on. Now let's see, let's load this into Scheme. Now, when you write this in Java, the key is to see that when you write this in Java, it doesn't look anywhere near this elegant. This is a very elegant way to do it here. See if I typed it in wrong, right? Okay. Here's all the outputs. Okay. Now, here's what I've done here. This block, well, actually, it's probably easier to look at it here. This block of code is using the slightly less sophisticated comparison factories. It's using the comparison factory of just one parameter. So this is a comparison factory for sorting by area, call this the same comparison factory. This is a comparison factory that sorts by population, but it only takes the ordering. This is what it would look like if I didn't use the factory methods. I would sort country, giving it a comparator, and there I'm writing out the comparator as if I didn't have a factory method. So this is what the code looks like when you don't use factory methods. In fact, here's how I should order this code. The code was ordered carefully. Okay, so here's the sort method. There's a get method for the area and a get method for population. Here's the sorts, not using any comparison factories. This is calling the sorts and building the comparator on the fly. Okay, that's very verbose. I have to build the comparators on the fly. The comparator is a lambda that takes in two countries, and it's going to compare them with less than on the area field of country 1 with the area field of country 2. Okay, now that's prone to error. There's a lot to type there. So then I say, okay, let me write two comparison factories. One for compare by area, one for compare by population. And then this code shortens a little bit to just this code. Okay, so I'm comparing by area with that comparator, or comparing by area with that comparator. But then I could shorten it even a little bit better. I don't really need two different comparison factories. I can just have one comparison factory that takes in two parameters, the comparator and the field. Okay, then I can write this really short code that says sort countries, comparing them on less than by area. Sort countries, comparing them on greater than by area. Notice that's a lot easier to read than this here.
It's a lot more flexible too.
It's a lot more flexible, and it's what we call declarative. This style of code is sometimes referred to as, I've declared. If you read this, it's really saying what it's doing. It's declaring things more than this. This code is declaring. It's kind of a weird term. This code tells you what it's doing. It declares what it's doing, but in a much more low level, very detailed way, saying how it's going to use C1 and C2, what it's going to do with this guy and this guy. This is a much more high level declarative, saying sort countries by comparing on less than on that get method. Okay, right? So now we'd like to mimic this in Java. Okay, we'd like to mimic this as much as possible in Java. And it is all mimicable in Java. Let me make sure I didn't type anything wrong there. I think I got things in right order. If I run this, yeah, there's all the outputs. You can, yeah, you have to kind of check that these are all, this is sorted. There's, I mean, I'm doing a lot of sorts. So I'm sorting 4 times here, 4 times here. And so there's 16 outputs here. There's 16 sort outputs, and you can check that they all did the right thing. Okay, so there's 16 outputs that, you know, but the key for our point of view is the way we've got this code to be more and more elegant, that we essentially writing it in a more abstract way by using notice how I'm using closures real well. Okay, like there's a very deep use of closure here. When I say make a comparator, I give the comparator these two parameters. The comparator returns to me the function that is the comparison function. So this guy is returning a function that gets passed to sort. Now, when this function returns, if you think in terms of stack frames, the stack frames are popped off and these functions are gone. These parameters are gone. But what's really happening is that this, when you call make compare, it's returning a closure. So this lambda, which has, I'm sorry, this lambda, the closure is that lambda. See, this function returns that lambda with the closure that includes those two parameters. Okay, so the closure, I don't have a way, the closure is that lambda expression. So make compare returns a closure that's that lambda expression along with the environment holding those two bindings. Okay, so when sort is called, sort gets that lambda expression, but it also gets told what fn means. Fn means whatever this guy's bound to. And it gets told what get means. Get means whatever this one's bound to in that environment. So this thing, without closures, I can't write these factories. Okay? See, these factories are the heart of modern functional programming is factories like these. Methods that build other methods so that you can parameterize behavior. We call it parameterized behavior. And it's making deep use of closures because the parameterized behavior is pointing at the actual behavior through its closure. This guy returns this parameterized behavior, parameterized by those two functions in their closure. It's tricky. It takes some getting used to, but it's the goal of modern programming is to write code like this. Okay. Now, what about Java? How does Java do this? Okay. Now, the answer is Java does this a gazillion different ways, depending on whether you want to write your code compatible with Java 4, 5, 6, 7, 8, 9, 10, 11, 12, whatever. There is an ultra-modern Java way to write this. So let's start with the ultra-modern Java way to write it. Actually, this is probably not even the most ultra-modern Java way, but it's a pretty modern Java way. Okay, I can't remember if this is the ultra-modern way yet, or if there's still, I think it might still be modifiable. Okay, I'm going to delete the comments so we can just look at the code, because it's actually, you can read the comments later, but I think if I delete the comments, it's a little bit easier just to look at the code and compare the code to the scheme. This is going to look pretty close to the scheme. Okay, let me just, let's just look at the code. Okay, now here's our data structure. It's a list of countries. The country's defined down here. So country is a private class. Okay, notice that unlike scheme, in scheme, I don't need to declare a type of country. I just say define countries is a list. I don't need types in scheme. That's a blessing and a curse. Some people love the blessing of it. Some people hate the curse of it. Remember, the curse is you could accidentally call a function with a data structure here that doesn't agree with the comparator here. Okay, you can end up with a runtime error where this guy and this guy don't agree on what they're talking about. This is a list of countries and this is a comparator of strings. Okay. Now in Java, to make that never happen, you have to be careful. You have to say, I have a country class. A country data structure looks like it's got 3 fields, it's got a constructor. This is where the verbosity of Java steps in. But this is where the safety comes in, because I'm specifying exactly what a country is, and I have to do it in this class. Okay, so Java knows exactly what a country is. Once it knows exactly what a country is, it knows exactly what a comparator of countries should look like. Okay, because you can't mix up a comparator of countries with a comparator of strings, because string and country are two different types. So here I have a list of countries, and then there's the elements, exact same thing. Okay, then I want to sort my countries. Okay, now here is the Java way of writing this kind of first. See here where I spelt out the comparators? Here I'm spelling out the comparator. Okay, so I'm sorting countries using a comparator. Notice I'm using modern Java lambda expressions, where you take two countries and you get the name of that country and you get the name of that country and you compare them in their natural comparison. So here I'm using their natural comparison, which is the comparison of strings. Okay, so I'm comparing, so I'm writing the lambda expression. So this line of code pretty much maps pretty closely to that line of code in Scheme. Call the sort function with the lambda expression that defines the sort. Okay, but then we'd like to do things with factories. See, there's no factory here. Oh, this just prints out the result for us. Then here I'm sorting with a different, remember over here, I sorted 4 times. Okay, so here is sort once, print it out. Sort a second time, print it out. So sort once, print, I'm sorry. Oh, I switched from countries.sort to, there's just, I called it a different way. Okay, so sort, okay, so sort, print, sort, 4 times, 4 different sorts, 4 different prints. Okay, so there's the equivalent in that block of code is the equivalent of this block of code. Doing the sorting without any without any factory method. Do the sorting without any factory methods. Okay, so there's the 4 sorts and their printouts. Okay, did I do all of them? Let's see. There's more. Oh, this one doesn't have any factory methods in it. Okay, so this one, I didn't implement the factory methods in this one. So this is using using Java's lambda expressions. Okay, but it's only doing this version without any factory method. So it's not showing how to write the factory methods. So it's using a modern style of Java for the sorting, but not showing you the factory methods. Okay, so there's the different sorts. Okay. Okay, so there is a bunch of different sorts. I'm sorry. There's a bunch of different sorts. Okay, 5 of them. There's a bunch of different sorts, but no factory method. Okay, so that's without it having any factory method. Okay. Here is another way of writing the same thing. Okay, let me get rid of the comments so we can concentrate on just the code. try to remember. Okay. This one uses the fact, so this one puts factory methods in there. Okay, so here's what it looks like with the factory methods. Okay, so there's the sort using, see, there's where I build this one. See, this one is like this one in Racket, where the factory methods take two things here. Okay, so see, I give the comparison factory a less than and a get method. See, and a greater than and then a get method, and a less than and a get method. Okay, so here's what it looks like in Java to build the. This is what it looks like in Java to build this kind of factory. So this guy here should be this thing here. Okay, let's see if we can make, try to line up the code and compare scheme with Java. Okay, so here's these 4 lines here. But actually, let me save this. Okay, actually, let me see if I can show them there. Maybe we can compare them. Does it fit in your screen? I mean, I have no idea what you're seeing. When I full screen over here, does it look okay on your screens?
Yeah, looks fine.
Okay, all right. So, okay, we're doing this version here. Okay, so here is sorting, and then you say we're countries. See, we're sorting countries. Here we're calling the sort method on the countries object. Okay, Java has a sort method in the list class. So I'm calling the sort method on country, and then I'm passing it the comparator. So here I'm sorting country, I make a comparison, and I give the comparison factory 2 parameters. And here now notice that the comparison factory here is actually an object. I say here, this is where Java becomes a little bit more verbose than Scheme. The make comparison is a function that returns a function. Java doesn't have, at least in this version of Java I'm using over here, this version doesn't have functions that return functions. It has constructors that construct objects that hold a function. So I'm actually going like 1 step back in Java. I'm not using the ultra modern Java here. I'm using a version of Java where my comparator is an object, and then my comparator factory is a constructor that constructs an object using those 2 functions. So these are function inputs, but this is a comparator of an object. Now here's the factory. The compare countries class implements the compare country interface. Okay, it implements the comparator of country interface. So it says this thing builds instances of things that compare countries. Okay, what does this object hold? Holds 2 functions, a compare function and a get function. I used S for selector. Here I used S for selector. Here I used get. And usually people call them get methods. Probably I should have called it getter here. Okay, so I use the letter S to mean a selector function. Okay, so then you have to have a constructor for this object. You say this comparator is that comparator, this selector is that selector. Then here's the compare method. This is the, we're implementing the comparator interface. Here's the method that we're implementing. A comparator of 2 countries uses the comparator thing, and it tests this object with that get method, and it calls the selector on the it applies the this is real hard to read. It applies the selector to country 1. Then it applies the selector to country 2. That's getting the fields. And then it tests the comparator with those 2 fields. Okay? Notice that job.
Doesn't code like this only really make sense to write when you want to write a whole bunch of different comparators for countries?
Yeah.
Like, wouldn't it typically just make more sense to say, this is how I sort, here's my sort function?
Okay, and then 2 years later, your boss says that's the wrong sort function. We have to change it. And then 6 months later, they go, oh, no, we need another sort function. Go change it. See,
so
what is the goal? Yeah,
maintainable.
the goal is, you're right. If it's a homework assignment, you're doing a lot of one-off programming. In the real world, what are you writing code for? The future. So you're saying, let's write the code in a way that's maintainable and versatile. So even though we only need 2 comparators, and it'd be real easy to write 2 comparators, we really ought to say, by the time the world ends, we may end up with 100 comparators. So we should be writing the code now to support multiple comparators. So in a modern programming environment, in a real world company environment, they're not going to probably be happy. You ever heard of the expression,
Minimum viable product?
Yeah, right. Okay. So you start with the minimum viable product. That's the code that says we need 2 comparators, so let's write 2 comparators.
Yeah, it's the simplest, easiest, fastest thing to write that will work and do what you need.
But won't necessarily be maintainable. And the other thing, you heard this phrase.
Technical debt?
Yes.
Never
what's debt?
heard of it.
Debt, oh, okay. What is debt? That's something you owe to somebody in the future, right?
Yeah.
When you write code in the minimum viable style, what you're doing is you're building up technical debt. You owe the good code later in the future. When the product needs to be expanded, when customer changes the requirements, you now have built into your code debt that you need to pay back because you're going to have to write, your code's going to be harder to maintain. The minimal viable product builds up technical debt. That's the way people will refer. You'll see this phrase used a lot when you start reading about programming in the real world. And there's a balance between these. Sometimes the minimum viable product can get you out the door and get you earning money. And then the money you earn can help you hire more programmers to pay off the technical debt. The technical debt is where you haven't written things the way it really should be. And that'll mean in the future, you're going to have a harder time maintaining the code. Okay. So you're right that, see, this code is more complicated. It's more complicated than I need to just have 2 different sorts.
Well, you're spending time writing an interface rather than actual running code.
But that interface makes the code more readable, it makes the code more maintainable, it makes the code more versatile in the long run. Yeah. Just remember, like over here, see, this interface made it much easier to read this. And this make compare function, now I can sort on all kinds of different things. I can sort on, any field I want, and I can sort in any, whether I want to sort by increasing, decreasing, and so I can actually make this as, this is more versatile. If somebody wants me to make a small change in the code, I can just maybe make a small change here instead of having to go back up here and make changes in, making changes in this is error prone. Going back and making changes here can be a lot more error prone than making a change here. Okay, so it's a style of programming. It's a style that's becoming more and more common of trying to write your code as generically as possible so that in the future, when it comes time to make changes, the changes aren't as hard to make. And you write the code generically by having it highly parameterized, and that includes parameterizing by behavior. So that includes things like this, where you parameterize the sort function with behavior, but the behavior itself is sorted by more behavior. So the sort function is parameterized by the comparator, and the comparators parameterized by little building blocks. It's like a Lego building block way of thinking of programming. These blocks build up the comparator, and the comparator builds up the sort function. Okay. Now, notice I need a lot of boilerplate to do this in Java. For example, look how elegant the scheme is. If I want to sort descending, or if I want to sort ascending, I pass the less than symbol. If I want to sort ascending, I pass the greater than symbol. This guy's an operator, and I can just pass him as a function. In this style of Java, you cannot pass operators. So I have to define an operator less than that wraps the less than operator. And I have to define a greater than operator that wraps the greater than symbol. Now, this actually got improved in Java. If I wrote this in a more modern style, I can actually pass the less than and greater than operators directly. Okay, and then I need to say my selector, which selects by country. Okay, notice that I already have a selector by country. It's the getArea method. See, there's the selector, getArea. So here I can say that my selector by area, which is the two-double function country interface, is the getArea method in the country class. Okay, it's a really weird style of Java programming. It solves problems, but it's kind of verbose and tricky to read. Okay, so here are my parameters to the comparator factory. These four guys here are things I can pass to the comparator factory. They are parameters. See, the comparator factory takes a bipredicate. This guy's a bipredicate. The comparator factory takes a two-double function, and these are my two-double functions. These classes here are defined in the function class, in the function package of Java. Java has a function package, and I'm using built-in function prototypes, and I'm declaring my parameters to the comparator using these prototypes. Okay? Okay, so this code now is pretty comparable to this code here, okay? To this code here. Notice that the factory method in Scheme is 4 lines. The factory method in Java is
a lot of lines.
Yeah, it's about 3 times as many lines. Okay, these 4 lines of Scheme are those lines of Java. Okay, I have to pre-declare what my types are for the parameter. See here, remember, if I don't get these in agreement, Scheme doesn't care. If this is a comparator of strings and this gets doubles, I'll just get runtime errors. The whole point of all this verbosity is that there's all these parameters in here. They're saying that this thing compares doubles, and everything's going to have to line up. Okay, everything's going to have to. Java's going to know when I build a comparator. When I build a comparator, Java's going to know that this thing and this thing agree with each other. I'm not going to be able to muck things up, whereas I could here. I could have something here and here that don't agree with each other. And this, because of all this type information, I won't be able to have this guy and this guy not make sense with each other. They should, all this boilerplate up here is making sure that this guy is compatible with this guy.
Could this static typing issue be solved by languages like Haskell, which will...
In Haskell, in Haskell, what happens is you write code that looks like that. And it ends up being
type checking for you.
Type inference. It does type inference. Yes. So you end up writing minimal amount of code like this, but it's as powerful as all this code over here. And that's what Rust and Haskell and the modern languages want to get at. They want the advantage of this code, which is type safe, with the advantage of this code, which is readable. Okay, so that can be done in some of the really ultra modern languages. Java's trying to get there. I should rewrite this in the absolute most modern version of Java, because Java actually, this is not the absolute most modern version yet of Java.
From
Now,
what I've heard, there's not a lot of adoption of the
nope,
super modern versions of Java.
because you have to start learning how to read. You have to start, yeah. If you're not, yeah, you have to learn it.
Like from what I've heard, Java 8, which is what we're using here, is the production version of Java.
Well, this is Java 8. Yeah, this is more or less this is kind of modern Java, but it's been improved even since Java 8, and then you get to ultra modern Java. I think I should try to rewrite this in a little bit more modern way. All right. Now, if you can also look at this from the point of view of old-fashioned Java. Okay. Now, here's a really old-fashioned Java version of this. Okay. So let me show you. Let's step through it real quick. There's the country class. Okay. I define it by its own class. So there's country. Here's my program that actually does the final. This is the program that runs. This is the one with the main method. It's going to create a list of countries. Then it's going to build a bunch of comparators. Okay, here's my comparator factories. Okay, so country comparator by name is a factory. So there's a factory that builds a comparator. There's another you see. So here's a bunch of different factory methods. And here I build 6 different comparators. This one compares by name ascending. This one compares by name descending. This one compares by area ascending, by area descending, by population ascending, and population descending. Okay. And then here I call the sort countries with the first comparator, sort countries with the second comparator, sort countries with the third comparator. Okay, so this looks pretty fine. I'm building 6 different comparators and then just using them. Okay, the work is in defining all those comparators. Okay, so here's one of the 6 comparators are each their own class file. Okay, so this implements the comparator of country interface. So it says how to compare a country. It takes in 2 countries, and notice it's hard coded what it does. This is not really, see, the comparator factory, I'm actually not, in this style, I'm not passing parameters to these factories. I don't actually have a real factory method. I actually just have one comparator for every kind of sort. So in this style, there is no real factory. Okay, so this is doing it like the old-fashioned way without even having a factory. So I actually build 6 different comparators. Instead of having a factory, I have actually 6 different comparators. So that's one old-fashioned way of doing it. That would be the equivalent in Scheme where we didn't use factories. That's the equivalent in Scheme of, that's how verbose this version looks in Java, where I'm not using any factory. I'm saying sort by that comparator, then sort by that comparator. Okay, so there's 4 different comparators. Here, there are 6 different comparators, and each one's defined in its own file. So that's a real verbose way to do it. There's no real factory method there. Okay. I think this one, let's see. This one starts being factory methods. Okay, so here's a comparator by area, but this is the Scheme version that used 1 parameter factories. So it's a 1 parameter factory that only takes the comparison, whether it's less than, greater than, less than or equal to, or greater than. Okay, so the factory only takes 1 parameter. Then here's how you would call this. This would be the comparison method here. So this folder is the equivalent of this folder here is equivalent of the scheme one that uses these one parameter factories. So it's a one parameter factory. Okay. Right. So but you can see it's a lot of code in Java. You have to write out those factories. I did 3 factories here. I only did 2 factories. I did by area and population. Here I do by area, by name, and population. So there's one more factory than there were here. But there needs to be a lot of code here to build up these different factories. So this does the comparison of countries using factory methods. So it's equivalent to this, but it's instead of just being 10 lines of code, it's a whole folder's worth of code. Okay, right? Then here are, let's see. I think these are the 2 comparator factories. Let me see. Yeah, no, let's see. Oh, this is just the same example, all put into one file. Okay, instead of breaking things up into multiple files, everything is put in one file. So here's the country class in here. Then here are so this file here is the same as this folder here, but everything's put into one file. So I took all the files in that folder and put them in one file. That's this one here. Okay, so it's built, there's no factory method. It's just building everything individual comparators. Okay. Then this one, same thing. There's no factory methods. The comparators are built using a slightly different style. But notice I'm hand building every one of the comparators. So every one of the comparators is hand built. Okay, so it's a slightly different version of this one. I can't remember what the difference is. I think it has to do with the way the comparators are built. Oh, I think they're inner classes. See, here the comparators are private classes. Here the comparators are inner classes. So it's the same code, but reorganized in a slightly different style of way of doing things in Java. These are inner classes sitting inside of main. These are private classes sitting outside of that class there. Notice Java has a lot of ways of skinning a cat. So these two are essentially the same code, but switching from private classes to inner classes. But the comparators are not built by factories. Then this one, they're using nested classes. Okay, so here it was using inner classes. Now it's using what are called nested classes. Okay, but I'm still hand building the comparators. They're not being built by a factory method. So I'm still hand building 6 different comparators. But notice Java's grown to be quite a large language. So this is private classes, inner classes, nested classes. But the same thing. It's still using, I'm hand building the comparators. Every comparator is hand built by itself. Okay, then go to another style of Java programming. Here I'm using
question about all these different ways of building these. Are there any substantial performance differences applying this to our parallel computing course?
I don't know. It's so hard to sort out performance in Java. My guess is not much. The difference between nested classes, private classes, and inner classes probably don't have a performance difference. They're mostly differences in style of coding. I don't think they
All
have
right.
performance differences. Okay, now this one, oh, what is this one? I forget what changed here. I think let me just look at one comparator. So here's the first comparator here, and here's the first comparator here. So here's the same comparator. And this is what you should do. Should look at the code like lined up. This is the first comparator, comparator 1. Okay. See, this is the selector. This one's selecting by name, and this is selecting by name. Here, the selector has been made generic. See, the selector is now a parameter. So, well, no, there's the get name. No, I say, there's country get name compared to, boy, I don't remember exactly what's changing here. I forget what this one does now. I forgot what this one does. Notice that what's changed is there's an extra parameter here. Notice that, see, that's the trouble with this code. The code is so verbose that it can be tricky to figure these things out. And then here, let's see, just real quickly. I've changed the way things are sorted. Yeah, I changed, yeah. The key is that you should, if you want to learn this modern style of Java, these are actually good examples to work through. I've tried to document them pretty well. It is a massive amount of code. You know, the thing is how Scheme, you know, a language like Scheme or Haskell, there's really just nowhere near as much code to read. You know, everything in Racket and Scheme is just done right here. It's all just right here. Whereas with Java, there's a bunch of different ways of parameterizing the key is, how do you want to parameterize the comparator? Okay, how do you build these factories? Java gives you a bunch of different ways of building the factories, and they're very verbose, and they're not necessarily easy to read, but they do give you a modern style of programming. They are what we're after in modern programming. And remember, this made a lot of use of closures. And if you go through the Java versions, one of the things to look at is where the closures are. And I make a comment here that you have to figure out where Java is somehow using something like a closure to make this work. Okay. Well, we'll look at these a little bit more detail on Wednesday, because it's run out of time now. But these examples are really good. This sorting idea, it's what a lot of people use sorting as the generic way to explain generic. You know, it's the generic way to say, I want to do something and parameterize it lots of ways. So the generic example of generics is sorting. It's the key. It was the first kind of function to get generics, just like in notice that. Remember, C already had it. You know, in the C language, you could see it was already there. Sorting was one of the first functions to start. People said, I don't want to write a gazillion sorts. How can I write one sort and use it over and over again? So that was the beginning of a very long story that led to a lot of code. So we'll quit there. And if you have questions, you know, please look at that code. The Java code, I'll see if I can reorganize it, make it a little bit easier to read. I've been working on this example for a few years, and I'm trying to make it so that this code is fairly straightforward as much as it can be. It is a lot of code, and it's progressive from one version to another version to another version. If you look at it carefully, it all makes sense. Okay, but I'll see if it can be. I'm not sure if I can make it a little bit more understandable. Okay, we'll look at it again some more on Wednesday. Okay, and right now should end the class because we went out over time. Okay, so if you have questions, let me know. Okay, bye.
All right.